All right, we're going to talk about two topics that we kind of missed just because of time. So I wanted to talk about polynomial inequalities and also rational inequalities. So I'm going to kind of abbreviate this set of notes, but I wanted you to at least be exposed to polynomial and rational inequalities. So if I sketch a polynomial function, like let's say we'll do a quadratic, or we'll do another quadratic, maybe a linear function, maybe a cubic function. This says, where did the function change sign from positive to negative values, basically your y values. See, my y values were negative here, and all my y values are positive. All of my function is positive. Negative y values, positive y values, they're all changing at their x-intercepts. So this just says that continuous functions will be important for calculus. So just a continuous function has no break in the graph. If it is continuous, it will cross the x-axis at intercepts of odd multiplicity. This is important because we're changing from negative to positive or vice versa. So the moral of the story is we should always check our x-intercepts. We want to figure out where is the graph above or below the x-axis, so we should check the x-intercepts. So the critical numbers are the x-intercepts of the polynomial, and the test intervals are basically the areas on either side of the x-intercepts. There might be more than one x-intercept. And basically, we could do this whole problem graphically. So I want to show you how I would answer this question graphically. Where is this polynomial less than 0? If I plug it in, x squared minus 2x minus 3, and I look at a graph of this function, where is that function less than 0? Wouldn't you say it's down here? So how do I explain to someone where this function is less than 0? I'm going to say that it's less than 0 between this x-intercept and this x-intercept. How would I find the x-intercepts? So where are the x-intercepts? I have to factor x minus 3 times x plus 1. The x-intercepts are at 3 and at negative 1. I just factored. So all a test interval is if I didn't have a graphing calculator showing me the graph, I would say, all right, I'm going to put negative 1 on a number line. I'm going to put 3 on a number line. I'm going to use open circles because this is a strictly greater than or less than inequality. So the x-intercepts themselves would produce 0. This does not say less than or equal to 0. It says strictly less than 0. So I don't want to include either of those in my answer. These are my 3 test intervals. Here, here, and here. I want to know if I plug in an x value, for example, negative 2, into this function, will it produce a negative answer? So when I plug in negative 2, what do I get? I get 4 plus 4 minus 3. So 8 minus 3 is 5. Nope, that is not negative. That tells me that this region is not part of my solution region. Give me a value between negative 1 and 3. How about 0? When I plug in 0, I get negative 3, and that's a negative value. So that's a good test region. That's the region on my graph that was below the x-axis, remember? So this is just proving algebraically that this is the region of x values that I would want. And when I test positive 4, I get 16 minus 8 minus 3 is, what, 5? That's positive, so I do not want this region of x values. So my correct solution is that, my correct solution is that x has to be greater than negative 1 or less than 3. Anything in that region, my graph is going to dip below the x-axis. So if you prefer to solve these graphically with a calculator, that's fine. I'm going to have you do, in a minute, example 2 and example 4 for practice. I just want to show you one more example together. So example 3, you cannot find x-intercepts unless you have 0 on the right side of your equation. So your first step would be adding 16 to the other side. So now you have 2x squared minus 4x minus 16 is greater than or equal to 0. And now to solve this inequality, my first step would be to divide by 2. So I'd have x squared minus 2x minus 8 is greater than or equal to 0. I divided everything by 2 on both sides of the equation. I'm going to factor x minus 4x plus 2. So my x-intercepts are at 4 and at -2. Let me show you how to do this graphically, since you've got a graphing calculator, so you don't have to go through all the steps of plugging it in. Basically, you're going to want to plug in this original function when it's greater than or equal to 0. So y equals 2x squared minus 4x minus 16. This is saying, hey, where is this function greater than or equal to 0? So where is this parabola above the x-axis? Here and here. How do I say that? Well, this is -2. So x has to be either less than or equal to -2 or greater than or equal to 4. So I'm just going to skip this step. Oops. Yeah, skip, did it graphically. So x has to be greater than or equal to -2, or x has to be, nope, that's wrong. X has to be less than or equal to -2, or x has to be greater than or equal to +4. And these have to be written as two separate inequalities. This is one region of the graph over here. This is a separate region of the graph over here. The reason that we could do the first one as a and inequality was because it was that region under the graph connected to itself. All right, so you're going to come back or you could finish right now, examples 2 and 4, and you do not need to do 5 and 6. On the rational inequality sheet, these also can be written as inequalities. So when I sketch a rational function, for example, I'm just making one up here, but here's one rational function like this. And here's another rational function. Let's say this time it's down here, and it's like this and like this. Where did that just cross the x-axis? At this asymptote, it jumped from negative to positive, and at this x-intercept, it jumped from negative to positive. So the critical values for rational functions are the x-intercepts and, this time, the vertical asymptotes. And those would form your test intervals. I would much rather just have you look at the calculator and answer the questions about solving this inequality, just so you're familiar with what this is asking you. All right, here's my rational function. It is less than or equal to 0, so I can go ahead and plug that into my y equals menu. Or if you want to practice graphing it by hand, good for you. Divided by x minus 5. Where is this graph below the x-axis? So it is below the x-axis right here. So let's think about our critical values. It has a 0 at x equals 0, right? That's its x-intercept. And it has a vertical asymptote at 5. So 0 and at +5. So this is 5, this is 0, and this is the region I want below the x-axis. So I'm just going to write graphically, and I want to be under or equal to 0. So I can include 0 as part of my solution, but I cannot include 5 because 5 is an asymptote. So my graph is never going to touch 5. So 0, it'll touch 0, and then all this spot is below the x-axis. So my solution region is between 0 and 5. I'm going to do let's just do example 2 and 3, and then you're going to do the problems that are at the bottom of the page. We're not doing these application problems just because we have too much on our plate and we're moving on. So, example 2. Let's look at it on a graph here. So we've got x squared plus x, plus x minus 6 divided by x. So where is this going to be greater than 0? Two different spots, here and here. So we need to figure out our x-intercepts because that's where it's crossing the x-axis. So to find out the x-intercepts, we'd have to factor the numerator. So I'm looking for the factors of -6 that add up to 1. So it would be at x equals -3, +2, and the denominator asymptote would be at 0. All right, we want all the values above the x-axis. So if this is my vertical asymptote, I go from -3 to 0. And if you want to do the test intervals, that's fine. So I go from -3. I want to be strictly greater than 0. So -3 is less than x, which is less than 0. That is the inequality that represents this region of the graph that's all above the x-axis, right? I start at -3, I go to 0, I'm not including the endpoints, and then here I start at +2 and I go forever. So I could say, or x is greater than 2. So I have two different regions of the graph, here between those two x values, and here extending forever in this direction. I'm always above the x-axis. So why would I want to do example 3? Because I need 0 on one side of the equation. So my first step, I need 4 over x plus 5 minus 1 over 2x plus 3 is greater than 0. I need all of this on the left side of the equation. I need to make a common denominator. If I already have x plus 5 as a factor, then this needs x plus 5 over x plus 5. If I already have 2x plus 3 as a factor, this needs 2x plus 3 over 2x plus 3. So my numerator, what does that become? 8x plus 12, 8x plus 12 minus x minus 5 all over 2x plus 3 times x plus 5. What's my real numerator? 7x plus 7. All right, where's my x-intercepts? This actually factors into 7 times x plus 1. So I've got something going on at -1, something going on at -3/2, and something going on at -5. I want any part of the graph that's above the x-axis, but I have to put it into my calculator as 4 over x plus 5 minus 1 over 2x plus 3. So see how I did it as my original fraction minus my other fraction? Where is that above the x-axis? It looks like it is all in this region and then maybe just in this region. So let's see, what was our intervals? This must be -5. This must be -3/2. So from -5 up to -3/2, I'm good. And then from -1 onward, I bet you that never touches the x-axis again. Let's go to our table setup and go to 100. Is our value still positive? Yes. So x has to be greater than -1. Those are my two separate regions. So you've got these 4 problems to answer about rational inequalities. I said no to this page. So you got 4, 5, 6, and 7. And you're also going to go back to polynomial inequalities and do example 2 and 4.